All right, today we're diving into one of the biggest, most mind-bending, unsolved mysteries in all of computer science and mathematics. We're talking about the P versus NP problem. This is a question so important, there's $1 million prize for anyone who can solve it, and an answer that could literally change the world as we know it. So let's get into it.
So to really get our heads around this, you have to understand that from a computer's point of view, not all problems are created equal. I mean, some are ridiculously easy, while others, well, others are just monstrously, fundamentally hard. And just look at the incredible difference here. On one side, you've got something like sorting a list of numbers. Your computer can do that in the blink of an eye. But on the other side, you have the famous traveling salesman problem. Finding the single, absolute best route for a delivery truck to visit 100 cities is so difficult that a modern computer would need billions of years to figure it out. Billions! So, what on earth separates these two kinds of problems? Well, computer scientists have a specific language for this stuff, a way to classify these problems, and it all boils down to two very, very important letters, P and NP.
First up, let's talk about P. P stands for polynomial time, which is really just a fancy way of saying solvable fast. These are the problems that we consider easy for a computer because we have a known efficient recipe, an algorithm, to find the solution directly. You know, things like sorting that list of numbers, or your GPS finding the quickest way to get you to work. Those are problems in P.
And then there's NP. Now, this is where it gets really interesting. Problems in NP aren't necessarily easy to solve, but, and this is the key, their answers are easy to check. The classic example is a giant Sudoku puzzle. Actually solving it from scratch could take you forever, but if I just handed you the completed puzzle, you could check if it was correct in, what, a minute or two? That's the core idea of NP. If you're given a possible solution, you can verify if it's right fast. Now here's the most crucial part of this whole thing. Every single problem that's in P is also an NP. And that makes total sense, right? I mean, if you can solve a problem quickly, you can definitely check a proposed answer quickly. You just run your fast solution and see if you get the same result. This simple fact that P is a smaller circle inside the bigger circle of NP is the seed of the entire $1 million question. Okay, so now let's zoom in on a very exclusive, very special group of problems that are lurking inside of NP. We're talking about the heavyweights, the absolute titans of computational difficulty. These are known as the NP-complete problems. You can think of them as the hardest of the hard problems inside NP. The members of this exclusive club include that traveling salesman we talked about, complex logic puzzles called SAT, and even things like finding a group of people on a social network who are all friends with each other. At first glance, they all look completely different, right? A logistics problem, a logic puzzle, a social network thing. But here's the big, mind-blowing secret of this club. In a computational sense, they are all the exact same problem, just wearing a different disguise. It's wild. If you could find a fast, efficient algorithm for any single one of them, you would have, in that same instant, found a fast algorithm for all of them. So how is that even possible? How can solving a map coloring puzzle somehow help you solve a package delivery problem? The secret sauce, the magic that links them all, is a beautiful concept called reduction. A reduction is basically a clever and, most importantly, fast recipe that lets you transform one problem into another one. It's like a universal translator for puzzles. It takes the language of one problem and perfectly rephrases it into the language of another without losing any of the important details. Let me walk you through it. Let's say you're trying to solve that clique problem, finding a group of mutual friends. Using a reduction, you can run a quick transformation recipe that turns your social network map into a giant logic formula. Now, if you had some magical, super-fast solver for logic problems, for SAT, you could just feed it your new formula, get the answer back, and it would tell you exactly where the clique was in your original network. You've used a solution for one problem to solve a totally different one. And this entire idea was unlocked back in 1971 by something called the Cook-Levin theorem. This was the massive breakthrough. It proved that these NP-complete problems even existed. And it established that first one, SAT, as the original member, the kind of Rosetta Stone that allowed us to find and connect all the others. And all of this brings us right back to the heart of the mystery, the question that computer scientists have been wrestling with for more than half a century. The question is this: are these problems actually hard, or are we just not clever enough to have found the secret recipe yet? Is the world of problems that are easy to check, which is NP, actually the exact same world as problems that are easy to solve, which is P? In other words, does P equal NP?
And this isn't just some academic thought experiment. It's one of the 7 Millennium Prize problems, and the Clay Mathematics Institute has a cool $1 million prize just waiting for the person who can prove it one way or the other. Now, it's important to say, while we don't have a definitive proof, there is an overwhelming consensus in the field. Pretty much every computer scientist you ask believes that P does not equal NP, that these hard problems really are in a fundamentally different class than the easy ones. But what if they're all wrong? What if P does equal NP? The world would change literally overnight. For starters, all modern encryption, the very foundation of internet security, banking, everything, it would all shatter instantly. But on the flip side, we could solve humanity's hardest problems perfectly, curing diseases by folding proteins, designing perfectly efficient supply chains, creating AI that could make unimaginable creative leaps. It would be a total revolution. So for right now, we all operate under the assumption that P is not equal to NP. Our entire digital world, especially anything that needs to be secure, is built on the belief that certain problems are just impossibly hard to solve. So if we can't solve them perfectly, how do we actually deal with them in the real world? Well, we get clever. We stop looking for the one perfect answer, which could take eons, and instead we use approximation algorithms to find answers that are good enough, or maybe 99.9% perfect. We use heuristics, which are smart rules of thumb that work great in practice, even if they're not guaranteed. It's all about being practical when you're facing down impossible complexity. And this is not just theory. This stuff powers our world every single day. Package routing for companies like Amazon, scheduling tasks in a microchip factory, designing networks, figuring out how proteins fold in biology. All of these huge industries rely on finding clever, practical ways to tackle these fundamentally hard, NP-complete problems. So you see, discovering that a problem is NP-complete isn't a failure at all. It's actually a huge sign of progress. It's a signpost that tells us, hey, stop wasting your time searching for a perfect, fast solution that probably doesn't exist, and instead, it guides us to focus our energy on developing the brilliant, practical workarounds that actually get the job done. And that leaves us with this final, tantalizing question. Is the difference between P and NP a fundamental speed limit of the universe, a law of computational physics that we can never break? Or are we just one brilliant idea, one elegant algorithm, away from changing absolutely everything? Right now, nobody knows for sure.